The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone, and welcome to the Research Results webinar. My name is Mike Fitch with the Ohio LTAP Center here at ODOT, and we appreciate your participation. As we get started, please take a moment to locate the questions box in the GoToWebinar panel. During the presentation today, please use the questions box to send in any questions you might have. Please note we will discuss all questions at the end of the presentation. Looking at the handouts section of the GoToWebinar panel, please note also that a PDF copy of the presentation is available for reference. With that, we will go ahead and turn things over to Sam. Hello.
Hi, Mike. Thank you. Hello, everybody. My name is Sam Corey. I'm Associate Professor of Civil Engineering and Director of ORIT at Ohio University. With me today is Dr. Eddie Chu, Professor of Civil Engineering and Director of the Transportation Systems Research Laboratory at the University of Toledo, and Dr. Mary Robbins, who was with Ohio University and currently is at a position with the Pennsylvania Asphalt Pavement Association. And today's presentation is a field evaluation of the perpetual pavement concept. As an introduction, we'd like to talk a little bit about the perpetual pavement concept. The endurance limit was started as a level of strain below which there is no cumulative damage over an indefinite number of load cycles. And this was the kind of definition of where strain limits are for the pavement. So we can see from the graph that the number of cycles, as the number of cycles increase, we have much thicker pavements that are more flexible. So this kind of gave the start of the perpetual pavement concept, in which multiple layers, each of which will serve to extend the lifespan of pavements and reduce the need for frequent maintenance and repairs. These would control the mechanistic responses to prevent damage. So we have fatigue damage, which is kind of the horizontal damage at the bottom of the AC layer. So each of the layers, the base course, the durable fatigue resistance layer, a high modulus rut resistance intermediate layer, and the high quality HiMA or others in the top layer of the pavement. And this is all out of the research by Dr. Newcomb. And also this would stop the rutting, so we would have the vertical strain deflection or stress at the top of the subgrade, controlling the structural rutting. So different materials with specific properties to resist different types of distresses. Of course, we have the fatigue cracking, we have rutting and cracking, and then we have low temperature cracking, and those are all illustrated in these kind of visuals here for your reference. So what was the I guess what's the problem statement? And I'm going to kind of stop back here for a second and kind of clarify something. So in the beginning of this research, we're using HiMA as our designation for the high polymer, highly modified asphalt that we were using. And this definition changed once the project started, and I'll explain as we go through. So while the HiMA sections performed well in the APLF, and the APLF is our Accelerated Pavement Load Testing Facility here in Ohio, and this research was previously done in coordination with ODOT. It was necessary to further explore the use of HiMA on an in-service pavement to validate the perpetual pavement design concept as it applies to this highly modified material. So there was a need to determine where in the cross section, throughout the base only, the surface only, or different layers, where could the HiMA be used to achieve the most cost-effective perpetual pavement. A little bit about the research background. Perpetual pavements introduced in 2000 by the Asphalt Pavement Alliance to address limitations of the Ashton 1993 design method The concept aims to prevent structural damage by controlling stress and strain through optimal layer thickness and material selection. There were several studies completed in Ohio. Ohio has been implementing studying perpetual pavement since 2003. In 2015, a study showed that pavements with at least 13 inches of pavement of asphalt on stabilized base meet the perpetual pavement criteria, while during that study it said thinner sections do not. In 2014, tests using highly modified asphalt with 7.5 SBC demonstrated improved resistance to fatigue and rutting, even in thinner cross sections. However, due to higher costs, further investigation is needed to determine the cost effectiveness of the use, and that was a report by Sargent in 2015. And then current research focused on high polymer modified HPM asphalt, evaluating its performance and cost effectiveness under Ohio condition. This includes assessing its structural layer coefficient and comparing it to conventional asphalt. So we can see that in 2019 and forward, ODOT designation for this material has become HPM, or high polymer modified asphalt, versus the HiMA designation from previous. Sorry. So this is kind of a review of the literature that was completed in Ohio. So in 2008, we had the first perpetual pavement, which was instrumented on Wayne County 30 highway. Maximum strains during that time were found to be 129 microstrains. In 2009, a study at the indoor testing facility using warm mix compared to traditional hot mix asphalt also showed the thickness, and at that point, the thickness layers were about 16.25. 2013, another study on US 23 route also showed the different thicknesses used. In 2013, Dr. Timms at NCAT also conducted some studies on the perpetual pavement concept. He had used the 5 3/4 highly polymer modified asphalt, designed with 7.5 styrene butadiene polymer, 7-inch asphalt sections containing conventional materials on the NCAT test track. Data was recorded over 2 years and over 10 million easels. Findings from this study concluded that neither section showed any sign of cracking, but laboratory tests showed a significant improvement in rutting resistance in the HPM asphalt. And it showed an estimated increase of fatigue life by 17 times that of conventional asphalt. Moving onwards with that, in 2015, we conducted the study in the indoor facility at OUL in Lancaster, and again, that contained 7.5% styrene, butadiene styrene, SPS. The measured strains were relatively low and generally fell below the fatigue endurance limits determined from NCHRP 9-44 model at 70 degrees Fahrenheit, 21 degrees Celsius, or 100 degrees Fahrenheit, 38 degrees Celsius. So the impetus for the current study that we're talking about came from a culmination of all these literatures and trying to figure out what is the most effective, cost-effective way of conducting the perpetual pavement. The goals and objectives of the study: the primary goal and objective are to design, construct, and instrument the first in-service perpetual pavement with high polymer modified asphalt in Ohio. And the reason for that is to provide a method for future designs. The task we were tasked with is to conduct a comprehensive literature review, to examine the current perpetual pavement concept, design tools, fatigue limit, and HPM properties, review all the data and assess the existing data from the perpetual pavement test sections in Ohio and other sections that included high polymer additive. Conduct a study and design the recommendations for the test section, proposed thickness, instrumentation, laboratory testing, plans for the HPM field study. Construction monitoring. Once this section are placed, we were to go ahead and conduct a material testing, collect and once that's completed, then follow through with data analysis and develop a structural layer coefficient for the HPM and conduct a cost-benefit analysis for the test sections. And at the end of this project, we were to provide guidance and training for ODOT to create a perpetual pavement design guide with recommendations and to provide the training for them. I'm going to go ahead and scroll through all these. So having all these tasks together in front of us, the methodology we pursued was in 5 phases. Phase 1 was the project site selection, cross-section design, material and thickness. Phase 2 was the construction, instrumentation, characterization of in-situ pavement material, both in the lab and in the field. So conducting falling weight deflectometer, DCP, collecting cores, conducting laboratory tests. In phase 3, we were collecting pavement response data from truck testing. Phase 4 was the analysis of all this data together. And then phase 5 was the evaluation of the perpetual pavement sections that we did. So I know, so this project started in 2019. And for those of us with some memory, we remember the shutdown and closures in 2020. So we kind of faced the issue of finding took quite a lot of time and a lot of coordination between the PI at the time, Dr. Mary, and ODOT and everybody else. So this was kind of a big endeavor given the circumstances that we went through with it. But either way, the decision was made to go ahead and instrument the section, northbound section of Wayne 83 in Worcester, Ohio. Worcester is in the northeast quadrant of Ohio. 83 was being repaved from the ground up, and so the route was chosen to put the 7 test sections in there. If you kind of were paying attention, you can see that in 2003, the first perpetual pavement was actually on Wayne 30, which was only a few miles east of this existing road. The cross-section design included the 7 test sections that kind of connected to the main line. So the main line included 1.5 inches of surface, 1.75 inches of intermediate, and 5 inches of base. The 7 sections that we had included section 7 as the thinnest section, all the way to section 1 as the thickest section. And section 7 included high polymer modified asphalt binder on the surface, intermediate, and in the base layer. Section 6 had the same surface and intermediate layers, except that we increased the thickness of the base layer by 3/4 inch. Section 5 was increased by a further 2¼ inches from section 7 and included high polymer asphalt throughout. Section 4 had conventional binder in the surface and intermediate, but high polymer modified asphalt in the base. Section 3 acted as our control section and was conventional binder from top to bottom, with the base layer being 9¼ inches thick. And then we kind of went to Section 2, where we included the high polymer section in the surface layer, and then Section 1 had the surface and intermediate as high polymer, and the base stayed as a conventional binder. Each section consisted of an instrumented section of it, and the rest of the 1,200 feet or so approximately were used to look at the performance. The instrumented section was basically 25 feet that included instrumentation in the center line outside wheel path and a foot in towards the shoulder. Instrumentations included H-shaped strain gauges at the interface between the subgrade and the base, pressure cells placed at the interface of the subgrade and the aggregate base, and then temperature sensors placed from the bottom up. The next, so we can see that the temperature sensors were at the bottom of the AC base, in the middle of the AC base, at the interface between the intermediate and the AC base, and at the interface of the surface and the intermediate base. These pictures kind of show our instrumentation. These are the pressure cells being placed on top of the subgrade. We had pull boxes that accepted all the wires coming out of these sensors, and then from the pull boxes we had above ground cabinets that housed the wires for permanent storage and access during testing. And then this is the placement of the strain gauges under the AC base layer. These were TML H-shaped strain gauges. They were placed according to manufacturer's directions. The strain gauge tamped and made ready for data collection. To characterize the in-situ pavement materials, we conducted FWD testing and DCP testing. FWD testing was conducted on the stabilized subgrade, aggregate base, asphalt base, and asphalt surface. So for each of the dates shown, the ODOT falling weight went and conducted test runs on the same locations. DCP was conducted on the unstabilized base, on the stabilized base, and then through the aggregate base afterwards. For the dynamic componentometer testing, as can be seen here in the picture, we took a core and then we went through the top. Basically, the 3 steps that we followed was to reduce the noise, which means disregard any blows with depth change less than 0.04 inches, convert the MR values to CBR, and then identify the uniform layers that we would have. All these were following the reference here cited 2007. So this picture kind of shows what we did with the DCP data, kind of normalized what a 304 base would be, and 304 is the ODOT designation for the aggregate base, and then through the stabilized base, and then going down through the unstabilized base as well. Summary of the DCP result gave us the average resilient modulus for the 304 base and the average resilient modulus for the stabilized subgrade. And from those numbers, we went on to get the CBR values for our analysis. So the falling weight deflectometer was conducted by the ODOT falling weight deflectometer machine. The operator went when the sections were ready, as previously mentioned, on the different layers as they were being built. So during pre-construction, we looked at whether the subgrade had uniform stiffness or not. And then data collected during the construction was to characterize the pavement layers. And then we also conducted FWD data prior to the controlled truck testing. And that's to try to get the modulus at the time of testing for our data analysis. The figure there shows also, what the FWD basin looks like and the sensors that were collected. So this shows the normalized D0 results for the stabilized subgrade. And if I can go back, the D0 is the sensor that's right under the load right here. And this is in mils per kip, so this is normalized for sections 1 through 7. And we can see the variation from the data here of the stabilized base. In general, they all fell within the same limits. This is the same data, but on top of the granular base, the 3 or 4 base, again, normalized. Again, we're looking for variation, and there's slight variation, but not really anything large to look at. And then again, this is the FWD results through the asphalt base and the normalized D0 as well. The bottom right here is the thicknesses of each of the base layers, and the C in front of it here designates that this was conventional asphalt at the thickness of 9 1/4. H meant high HPM layers, and these are the thicknesses of each of the HPM layers. And then again, this is the normalized D0 data for the asphalt surface. And on the x-axis for each of the 7 sections, we can see the combination, the total thickness and the combination of various layers. So HHC would mean that it was polymer, and then conventional, all the way to section 7 right here, which had 3 H's in it and at 8 inches. So again, 7 was the thinnest section. And then, at least on paper, and we'll discuss this a little bit later on, sections 1, 2, and 3 were supposed to be the same thickness. So in 2010, there was a report written by Edwards and Figueroa that looked at the FWD data and the performance of test sections, and this was based on the LTPP test road on US 23 in central Ohio. And the data looked at the ratio of D0 versus D60 and to predict the performance of it. And this was kind of done as an analysis point to look at this ratio. So we can see the cluster of sections that were in the 12.5 being clustered in the good performance section right here, where the sections that had 8 1/4, which is section 7, was kind of clustered towards the fair and poor performance as predicted by the falling weight, and kind of the conventional section with 10 1/2 was in the fair rate, and then the high polymer section at 10 1/2 was in the fair to good performance region. Again, this is from the D0 to D60 ratio, which was by Edwards and Figueroa. Once the testing was complete, we conducted deep coring to get cores from all the sections. This also allowed us to conduct DCP testing as well, but it also allowed us to take these cores and conduct testing with them. So for each core that we received, we measured them. Cores were documented. We looked at the site profile to see if we can identify any segregation, other issues that might have happened during construction. So right there in front of you, you can see the base core. And then we have the full depth cores from sections 1 through 7, brought them back to the lab, and we were measuring them to make sure that the thicknesses as designed were thicknesses as built. And this is one of the first things that that came up. So from the measuring all the different cores, we can see section 1 was 9 inches of asphalt base, 1.85 for an intermediate base, and 1.5 for surface, for a total core thickness of 12.3, while the design total thickness was 12.5. Section 2 had 10.2 inches for asphalt base, 1.75 for intermediate, and 1.4 for surface, for a total thickness of 13.3, and a total design thickness of 12.5. So this is kind of the biggest discrepancy here of thicknesses. I just want to point out that none of these fall outside ODOT specs, except that section 2 was over-designed, and the contractor gave ODOT more material than originally designed for. The asphalt base in section 3 was 9.4 inches, intermediate 1.8, surface 1.4, total thickness 12.5, design thickness 12.5. And again, section 4 had a 7.1 asphalt base, 1.83 intermediate, 1.5 surface, total thickness 10.4, total design thickness 10.5. Section 5, same numbers, total core thickness was 10.4 and total design was 10.5. Section 6, thicknesses was 8.8 and total design thickness was 9. And section 7, total core thicknesses were 8.3 and that design was 8.25, 8.25. And the numbers in parentheses are in millimeters, just in case you're interested in those numbers. So at this point, the sections were designed, all the layer thicknesses. The contractor went ahead and built those sections. We collected samples for lab testing. We did some in situ field testing, falling weight and DCP, and we come to the phase of looking at the pavement response data. So with the help of the Wayne County Garage here in Wayne County for ODOT, we had 2 trucks, a single axle dump truck, which you can see on your left, and the tandem axle dump truck as seen on the right. So those were used in different tests to conduct the testing here for the truck testing. Measurements of the trucks were done. We documented the tag number of each truck so we can try to use the same truck for each of the tests. And then the weights given. So we conducted testing in May of 2023, August of 2023, November 2023, and again in May of 2024. The tire pressure was also measured in all the tires, and that's given in the table below for the single axle truck, and then the weights are given in the top table. So one of the things I'd like to point out is that in May of 2023, we went a little bit overboard in terms of the weights of the truck, and you can see that that truck was heavier than the other 3 tests that we conducted. And it's the same thing with the tandem axle truck. Checked all the tire pressures and weighed all the tires. And again, the testing in May 2023 was heavier than the rest. And this is kind of the average of the axle weights and so on. So 30,000 on a single axle for May 2023, and then we went down to about 27,000 or so for the other 3 tests. Same thing with the tandem. We started at 47,000, went down to 40,000 for the other tests. This is just a sample of the data that we got from the strain gauges. This is the transverse and longitudinal gauges on section 5, a single axle truck at 5 miles an hour. This was, this is only 2 seconds worth of data, but we were collecting data at a high rate, about 2,000 samples a second, and then filtering the noise. This is kind of the data looks that we get. And this is the same thing on section 3 for the tandem axle truck. And you can see the tandem tires back here for both the transverse and longitudinal strain gauges. So this graph shows the normalized transverse strain, the results for all test sections at 5 miles per hour. So this was normalized to 9 kips per inch of thicknesses. So, and then in parentheses, if you can see, we took the actual core thickness as opposed to the design thickness, and looked at the data and normalized it for each of the tests that we conducted May of 23 through May of 2024. And as expected, we can see that the high strains are in the thinner section, section 7. And then section 2, which was kind of the thickest section, had the lower strain readings, although section 3 is kind of close behind. And we did the same thing on the longitudinal gauges. Again, normalized the microstrains per 9 kips per inch of thickness. And again, you can see that section 7 kind of gave us the highest numbers, and sections 2 and 3 kind of went down towards the lower number because of the thickness. And then this is kind of, showing kind of the same thing. This is showing the maximum longitudinal tensile strain for each section for a 5 mile an hour controlled vehicle test, normalized per inch of pavement. And again, we can see that section 2, which was the thickest section, showing us the lower strain values, and section 7 showing us the higher strain values. And again, this graph is a normalized data for the transverse strain. One of the important things that kind of affects these numbers is temperature. And so this is kind of a record of temperature data from section 5, T1 through T4, basically down from the bottom of the base layer to the interface between the intermediate and the surface layer. And you can see the variation in temperature on section 5. So a couple of things to kind of mention here, and if you read the report, you'll see this. Section 5 was the most open section in terms of access to sunlight. The remainder of the sections all were covered with trees, so the temperature never really rose to be too high because of that tree cover and the shading that you got in the summer. Even though with the as open as it is and as hot as testing was in August of 2023, where basically the top of the surface layer reached above 110 degrees Fahrenheit, almost 120 degrees Fahrenheit, you can see that the base layer temperature never rose above 90. And there was a lag between that temperature of the surface versus the temperature of the base. And base temperature didn't reach 90 till almost 8 o'clock at night. And the testing that we conducted was actually done in the morning through the afternoon. So it actually never reach, and we started our testing at equality right around 10 o'clock, and we ended the testing somewhere around 4 or 5 o'clock right here. So just because of this lag and the nature of where this pavement is, we never reached really high temperatures in the base layers. And then we also plotted the normalized tensile strain as a function of pavement temperature to look at the effect of thicknesses and strains. And again, it's the same kind of graph that we see where section 7 has the highest numbers, and section 2 with the thickest has the lowest numbers as well. Now we go into lab testing and trying to characterize the lab material or the material from the field in the lab, so we are able to provide ODOT with values they can use in their future design. The set of tests that was conducted included dynamic modulus according to AASHTO T342 and T378, creep compliance and indirect tensile testing, AASHTO T322, Cantabro testing, which was AASHTO T401, ideal CT, ASTM D8225-19, Hamburg wheel test tracking, T324, and tensile strength ratio, T283 with ODOT supplement 1051. So the dynamic modulus measures the modulus and their varying temperature and frequencies. It's a required input for pavement ME design. The creep compliance is a measure of creep and susceptibility to low temperature cracking. Cantabro was a measure of durability. The ideal CT is a measure of cracking susceptibility at intermediate temperatures. Hamburg wheel track testing is a measure of rutting susceptibility and stripping potential. And then the tensile strength ratio is a measure of moisture damage and susceptibility. So the tests were conducted on base, intermediate, and surface layer. So we did that for the Cantabro dynamic modulus, ideal CT, and TSR. Hamburg wheel track testing was only conducted on the intermediate and surface layers. Does not make sense to run that on the base layers. Creep compliance was done on the surface layers, and indirect tensile strength was also done on the surface layers. These are the results of, I guess this is the samples as they came out of the Cantabro testing. And then we can look at the mass loss per as a percentage. So we can see, if we look to the furthest to the left, the comparison of the surface layers between the HPM surface versus the HMA surface, and we can see the HPM surface lost 2%, whereas the HMA surface lost 3% of its mass. The intermediate, we had a 2.5 loss for the high polymer sections versus 4.8% for the HMA. And in the base layer, we had a 5.6% loss on the HPM versus a 7% loss on the HMA layer. Hamburg wheel tracking, again, was conducted. This is the setup that we have in the lab to look at rutting. And we can look at the rut depth of the HPM surface versus the HiMA, the HMA surface, the conventional. And we can see that the HPM layers had less rutting than the HMA surface mixtures. And this is kind of the like accumulation of the rutting that we have. So the HPM surface, versus the HMA surface, and the HPM intermediate versus the HMA intermediate. And the green is at 5,000 passes, and then 10,000 passes, 15,000, and 20,000 passes. And again, that's the 2.25 millimeters or so for the HPM intermediate versus about 3.5. for the HMA, and then the HPM surface about 2.6 versus 3.25 millimeters for the HMA. Ideal CD was again conducted on the base, intermediate, and surface layers. And then these are some of the raw data graphs, I guess, that show the stability versus flow. It's kind of a telling. Those results were kind of summarized in here, where we can see that the CT index for the HPM layers were much higher as expected than the HMA layers. The TSR, tensile strength ratio, was also conducted on the base, intermediate, and surface layers, both in the dry and wet conditions. And then again, the lab results showed that the HPM surface, intermediate, and base layers were better than the HMA in terms of laboratory test results that we received. And then this is the strength in PSI of both the HPM and HMA surface, intermediate, and base layers. This is the creep compliance and the direct tension testing. Again, we can see the difference between the HPM and the HMAs. For the PG 88 minus 22, the higher DT value means we have lower stiffness and more strain. And for the HMA, lower DT value means more stiffness and less strain. And that's kind of what is shown in those graphs. This graph, at least this plot, shows the creep compliance at a 50-second average. Again, the HPM have higher values than the HMAs. And you can see the different temperatures that were tested at, minus 20, minus 10, and 0 degrees Celsius. Tensile strength testing as well showed the higher strength ratio, minus 10 degrees Celsius for HPM versus HMA. And from all these testing, we conducted the dynamic modulus and built the master curves for the surface mix, the intermediate mix, and these were used in our and as well the master curve for our base mix, and these were all used in our analysis. So this is kind of going to end the lab testing portion, the setup portion, and I'm going to hand it over to Dr. Chu to talk a little bit about the analysis and the structural coefficients.
Thank you, Sam. Yeah, could you move to the next slide, please? So from the previous discussions, most of the laboratory testing indicates that HiMA or HPM material, high polymer material, is tougher than the conventional material. However, from the field test, from the falling wave deflectometer test, deflection-wise, the material itself doesn't contribute that much in terms of reducing the deflection. So in the back calculation, doesn't cause a big difference. Yeah, thank you. So it's actually the thickness tends to control how the deflection behave, pavement deflection is higher or lower. And there was also a lot of variation within each section. Could you go back to the previous slide, please? Thanks. So in the proposal, we developed the using different approach to estimate the layer structure coefficient for the high polymer material. The first approach is to use the elastic modulus back calculated from the following weight deflection, measure at the weight 83, test pavement sections. We also use the dynamic modulus. This is the AASHTO, because the concept of the layer structure coefficient is an empirical AASHTO design concept. So this equation shown up here is used to estimate structure coefficient based on the elastic modulus or resilient modulus of the asphalt concrete surface layer at a given temperature. Next, please. So this is the modulus, back calculated surface layer modulus from following weight deflections. As you can see, it kind of varies. Presumably section 1, 2, and 3 have similar thickness. They are the thicker sections. They should have stronger deflections, but the reason it's showing up here is the conventional. The section number 3 is the control. It's convention. Both the surface, intermediate, and base course are conventional. They actually have higher modulus than the section 1 and 2, which use the HiMA. Section 1 use HiMA entirely, and section 2 use HiMA for the surface intermediate course. And so, yes, and this is the back calculated layer modulus base course. For the base course, it's also kind of has a lot of variation within each sections. There is no obvious higher for the HiMA versus the conventional material. So this table shows that if the elastic modulus or the resilient modulus increases, and the corresponding increase in the structural layer coefficient using that formula, which will give you the same, in order to have the same structural layer coefficient multiplied by thickness, thickness will reduce. And if we use the same thickness, divided by, so in terms of the ratio is that the thickness will reduce given that higher modulus. Modulus value either back calculated from following weight deflection or measured in the lab shows the modulus of high polymer mixes are similar or smaller than the control conventional mix. Therefore, based on this approach, it's not justified to increase the structural coefficient of high polymer asphalt to be higher than that of control or conventional asphalt concrete. The approach number 2 was to use the AASHTO 1993 AASHTO design guide section 5.4.5. This approach estimated the structure number above the underlying layer that's required based on the following weight deflection. The following weight measurements were taken on the surface of the stabilized subgrade, aggregate base, asphalt base, and asphalt surface when each layer was placed. Using the following weight deflection on the surface of the stabilized subgrade, assuming a 2-layer system with the stabilized layer as the surface layer, the modulus of the unstabilized subgrade was estimated from the deflection. The structure number effective structure number contributed by the stabilized subgrade was determined. The contribution of each layer above the stabilized subgrade to the structure number was determined in the subsequent way by the subsequent deflections. So the result shows that the structure coefficient using this approach for the 7 sections, as you can see, the surface intermediate course are higher than the asphalt base course. And these are the structural coefficient using this approach. They are actually quite high, right? They are way higher than the structural coefficient of 0.43 that's currently used. This just now, the deflection here is temperature adjusted, but also they have a lot of variation within each section. So this is like an average value of the deflection. So you can get fairly high structural coefficient for the surface intermediate course, and also even the asphalt base, they are also way higher than most of them are higher than the 0.43. The third approach was to compare the laboratory testing result to see if, obviously we already saw from the Hamburg wheel track test for rutting performance on the left side, the rut that developed after 5,000, 10,000, 15, and 20,000, they are all lower than the for high polymer mix than conventional hot mix asphalt mix. When we plot this data on the right-hand side, as you can see, the number of low repetition, the rut that developed on the high polymer mix after 20,000 low repetition is almost the same or equivalent to the rut that developed on control mix after about only 1/3, 6,700 low repetition, indicating potentially a threefold increase in rutting resistance. Next, please. So the previous Hamburg test is for rutting resistance, and the ideal CT test is for determining the cracking resistance. With a fracture mechanics-based parameter called cracking tolerance index, a larger cracking tolerance index or CT index indicates better cracking resistance. So on the right-hand side, you can see the CT index is higher, or higher the better. So it's the high polymer AC or HPM is having better cracking resistance for both surface, intermediate, and base courses. The tensile strength of the two different materials, these two materials, the high polymer mix also is higher than the control mix. The tensile strength ratio also shows better performance. So overall, the material is just displaying better tensile strength, tensile stress resistance, and therefore relate to cracking resistance. Other contemporary tests, mixture toughness test, use a LA abrasion machine to estimate mixture durability by the percent mass loss after 300 revolutions in the drum. And again, previously already shown, high polymer mix have significantly less mass loss than control mix. Creep compliance, tensile creep compliance is the ratio of time-dependent strain divided by constant applied stress. So under the constant stress, the creep compliance is the reciprocal of elastic modulus. Higher creep compliance means lower elastic modulus is desirable at low temperature to resist cracking, while lower creep compliance is desirable at normal temperature to resist rutting. So essentially, this is saying the temperature susceptibility, which is a problem for all the asphalt material, asphalt concrete mixes, is less. So in other words, a high polymer mix has less temperature susceptibility, right? It's less likely to crack at low temperature and less likely to rot at higher temperature. Dynamic modulus is the performing the test in the laboratory show that dynamic modulus of high polymer mix are smaller than that of control mix in almost all cases. So overall, the laboratory testing result confirmed with previous research that high polymer mixes have higher resistance to rutting and cracking than control mixes. The modulus and tensile strength of high polymer mixes are lower than that of control mixes. This indicates that high polymer mixes are not stiffer, but they are tougher than control mixes. The higher toughness of a high polymer mix enables it to withstand higher strength without fracturing compared to control mixes. Next, please. So the next approach, we use the field testing result at WEN 83 test pavement. That includes both falling wave deflection and strand measurement. The falling wave deflection test conducted at the WEN 83 pavement show that pavement deflection is primarily influenced by the total pavement structure thickness. Thicker pavement sections have smaller deflection. For pavement sections with similar total thickness, whether high polymer mix or control mix was used, does not have noticeable impact on deflections. Strand measurement of high polymer mix layers show higher strand than strand of control mix layers. As mentioned earlier, the higher toughness of high polymer mix enabled it to withstand a higher strand. So on the right-hand side, as you can see, this already shown sections 1 to 3 has thicker pavements than section 4, 5, 6, 7. This is the average deflection, because deflection actually vary quite a bit within each section, but we took the average of each deflection. As you can see, section 7 has the highest deflection, the lower curve. This is a scale that lower curve means higher deflection. And the top curve has lower deflection. So basically, it's dictated by the section thickness rather than the different material that's included in each section. Next, please. The next approach we decided to use was based on the actual pavement performance, because it's empirical design, parameter empirical design approach. So we feel these important to use the empirical result. The fifth approach uses actual pavement performance to estimate a structural coefficient. This is a preferred approach to require long-term monitoring of pavement condition, PCR distresses, pavement ride quality, and so on should be monitored. Also, we, in order to be a fair comparison, the actual traffic loading, in terms of the number of ESOLs and seasonal variation of subgrade modulus probably should be monitored as well. The control section is necessary for comparison. Lacking those information, we use the existing high polymer pavement sections in Ohio. Those sections typically are short stretch and used on high traffic volume area. So in surface pavement section rehabilitated with high polymer mix surface intermediate courses, potentially could extend pavement surface life. Now this is an overall result. I already jumped into the conclusion on the lower left, but if you will look at the right-hand side figure here, the orange and the black were existing pavements that was with the high polymer surface intermediate course. The two black ones, the Ashland County, they only have high polymer mix in the surface course. So they actually perform very poorly. The blue line represents the average flexible pavement performance of 50 and 60, activity 60 and 60. One performed very well up until the most recent year, and the other one started performing somewhat poorly. The difference between these two was that I believe the one that's performed better had a poor underlying conditions, so the pavement was thicker. So I think they were using thicker pavement for the better performing one, because the underlying condition was poor. before overlay. So overall, as you can see, these pavements we only have 2 years of PCR data to look at it. Taken as an average, potentially they may extend the pavement life. You extend the orange line could extend the pavement surface life by about 3 years, or 25% of the normal anticipated surface life of these general system pavements, based on limited data. Continued monitoring of these in-surface pavements and the test sections at the WAN 83 would be necessary to confirm this projection. Based on if we need to come up with a structural coefficient using the AASHTO design equations, right? So we could use this approach. This graph shows that if we assume the high polymer layer structural coefficient for different structure number, and assuming the thickness of the high polymer ISC is 3¼ inches, and the horizontal axis is observed percentage increase in lifespan. So this is the actual observed performance, because in AASHTO they use present serviceability index, but in ODOT we already switched that to PCR. So therefore, if we look at a PCR, if you do have extension in life, let's just assuming it's 25% extension. So the bottom shows observed percentage increase in lifespan of 25%, and assuming a structure number of 6 in this case, which is fairly thick pavement, and the surface layer is 3¼ inches. We can estimate the structural coefficient to be here. It's about roughly 0.485, so 0.48 or so. Which is higher. This is in comparison. As you see, the other curves converge to, at the left side axis, it's 0.43, which is in comparison to the currently assumed 0.43 structure coefficient. So this is relatively to the existing 0.43 structure coefficient. It's about 0.05 increase, right? Next, please. But if we use, so the previous one, we have to assume a surface intermediate course that's using a high polymer mix. So if that's only 2½ inches, then you will end up with a different chart. So the assumptions is that what is the surface and intermediate course combined? So this will be a thinner pavement, and therefore, if you have a 25% increase, you may or may not get that kind of structural layer coefficients, but still get somewhere around anywhere from 0.5 to 0.48 is what you will probably get. Next, please. Yeah, it's even thinner pavement. So in this case, at a thinner pavement, again, 25%, you will have a lower structure number as well. So you will get also somewhere in that range of 0.48 to 0.50. Next, please. So high polymer mix versus regular conventional AC mix in pavement design. PCR performance of existing in-surface high polymer mix pavements indicate potentially perhaps 25% longer surface life compared to regular AC pavement. A layer structure coefficient of 0.48 to 0.5 may be used for high polymer mix versus 0.43 for regular conventional mix, allowing for thinner pavement, especially in areas such as under bridges. The recommendation, further long-term monitoring is needed before reducing pavement thickness for cost savings, as longer surface life benefits likely outweigh cost reductions. So Particularly from the field performance, we realized that we probably should not reduce the surface intermediate course because we are using high polymer mix, because they don't perform very well. You need to give, even this material very tough compared with conventional material, you need to give them enough thickness for them to perform well. Next, please. The next is the benefit versus cost of high polymer mix. Benefits, it's better distress resistance, provides better resistance to rutting and cracking. In this study, high polymer mix lasts roughly an estimated 3 times longer against rutting in hamburger wheel track test. Cracking tolerance index is up to 114% higher compared to regular AC. Longer lifespan research show a 26% cost saving with high polymer mix due to less frequent maintenance. This is from previous research. Based on limited the PCR performance data, the high polymer mix overlay. In Ohio, most of them are just overlays, so just only the overlay thickness. In surface pavement did not have any full depth high polymer mix pavement. So just based on the overlay, high polymer mix overlay can achieve a 25%, roughly 25% longer service life. High polymer mix pavement may be thinner while maintaining the same performance as conventional AC pavements. The high polymer pavement mix itself costs about 10 to 20% higher for surface course and 10 to 15% higher for intermediate course than regular conventional AC. This is based on limited, again, very limited amount of data, but this is gives us a ballpark of that the performance, again, probably is more than the cost increase for the mix. As of course, when the high polymer mix is widely in use, the cost probably could come down. I'll pass back to Sam.
Thank you, Dr. Chu. Conclusions and recommendations. By the last time we went to the site, May 2024, all test sections were in excellent condition with no distress. Low strain values supported by stable pavement temperature due to the tree cover that I mentioned before. The strain performance, strain values remained well below the endurance limit. Despite the polymer's flexibility, we also have a strong 304 aggregate base and stabilized subgrade. Those also kept the strains very low. So if we look back at our results and look at the resilient modulus from falling weight and from DCP data, we can see that those were high values of resilient modulus for the 304 and the stabilized base. The polymer increased the flexibility, but didn't significantly affect strain due to the base strength. It allowed higher wrap content, improving crack and rut resistance. So one of the things that we have to mention for this study, and that's in the report, of course, is that the high polymer mixes had 35% wrap, whereas the conventional mixes had 20% wrap. And the base actually had, there was a higher percent mix, wrap mix in the polymer. Lab testing confirmed polymer improved flexibility, lower modulus, and boost resistance to cracking and rutting, just as Dr. Chu had mentioned, and the tests were all following AASHTO and ODOT protocols. HPM mixes are 10 to 20% more expensive, but if they extend pavement lifespan by 25 or roughly 25%, so that would be 12 to 15 years longer, which would make them cost effective over time. And then although a higher structural coefficient of 0.48 to 50 may be used for HPM due to its better resistance to cracking and rutting, HPM pavement surface and intermediate layer thicknesses should not be reduced. We're still at 1.5 to 1.75 inches for either one. That's pretty thin. And then we've recommended design inputs for HPM and conventional materials to be used with the Asphalt Pavement ME, and those were given in the report. We're researchers, so one of our recommendations is more long-term studies are needed to verify service life and performance beyond the PCR of 65. We need to broaden the cost analysis with larger, more representative HPM projects. And then we want to investigate the potential cracks between layers due to stiffness differences, and then further explore the interaction of high polymer with high RAP content. So those were our recommendations. Before we go to the questions, this was a long project. It took the coordinations of many, many people and the hard work of a lot of people who are not mentioned here as well. We would like to mention Jill Martindale and Jennifer Spriggs, who were from the Office of Statewide Planning and Research and put up with us for the last 4 years or so. From the Office of Pavement Engineering, Greg Lennefeld, Patrick Beal, David Miller, William Freeman, Adam Au, and Andrew Klaus. From the Office of Materials Management, Eric Beal and Jacob Luttinen. The Office of Construction Administration, Julie Miller. The Office of Technical Services, Sandra Maple. District 3, which is where this project was. And I'm going to butcher the names, I apologize. Mike, Scott, Eric, Scott Jenkins, and the staff and the crew at the ODOT Wayne County Garage, which were, none of this would have been done without them. The design and build team of E.L. Robinson and Kiko's and Construction Company. All the students from the University of Toledo and Ohio University that worked on this project, and the contributions of Dr. Mary before she went to her new position in this. I'd like to thank you and like to address the questions that were posted. And Mary, if you don't mind heading to question number 1.
Sure. Yeah, I was actually trying to move some things over to present if I needed to explain. So I can, if you don't mind giving me control, I will throw up a quick slide.
You see here.
The first question was, how do we design these sections? So great question. Let me show my screen. I want to make sure I'm showing screen 2. So I'm going to go quick. There we go. Okay, so Sam mentioned that there was a number of different perpetual pavement sections that had been constructed in Ohio. Kind of the way those originated wasn't necessarily rooted in a perpetual pavement design concept. And so we kind of evaluated all the designs, all the existing pavement sections, and we decided to look at this perpetual pavement cumulative strain distribution that had been developed at the NCAT test track. Dr. Richard Willis did this as his dissertation, and what he found and what you're looking at right here is all the work that he did in developing a threshold. And so we had a number of sections at the NCAT test track that cracked and many that did not. And when we looked at the cumulative strain distribution from the field measured strain, there tended to be a pretty large gap, and that's the hashed area here, between those that cracked. So everything to the right of this hashed area here cracked, and those to the left did not crack and actually were behaving perpetual. So from that, they launched, and I was part of this work, is we took those strain distributions and those cross sections and put it in per road, and then we developed a new cumulative strain distribution that you could then use in per road moving forward. So what we did is we looked at that, and then we evaluated the parameters that we had and the existing cross sections that we had in Ohio, and created our own new strain distribution that had been calibrated to cross sections that we knew were behaving perpetually past cross sections. And that included the work that was done in the APLF with the highly polymer modified material, and then also one more recent section that was done in let's see, it's part of the 2015 report. So I think it was constructed in 2012. And so that's what we did. We developed a cumulative strain distribution that was calibrated to Ohio test sections using material properties that we had. So what you're looking at on the screen was actually developed using back calculated modulus. We used dynamic modulus because we had more of that data, more consistent data in that way. Does that address question 1? Did anybody else? I'm not hearing anything. I guess you can't speak. You can only type fast, Johnny. All these questions are from Johnny. So the third question, well, let me answer question 2. The other question was what test temperatures, I'm sorry, what test speeds did we do this at? And that was at 5, 35, 50, and 55 miles per hour is what we did the controlled vehicle loading test. How were the strain measurements used in the analysis? Good question. So I think, Johnny, you also asked if we actually did any bending beam fatigue testing. We did not. So the way that we looked at the strain measurements is we were comparing it back to our cumulative strain distribution that we used in design. And we also, I did some work in taking those strain measurements that were made in the field and extrapolating it based on those temperature strain relationships that I could develop from the measurements that we did have. So mind you, the material that the conditions under which we tested weren't reflective of maybe the extreme temperatures. As Sam mentioned, we did have some cover that did prevent maybe getting some of those extreme temperatures in the measured data. And so I extrapolated out and compared it back to those sections that we knew behaved perpetually on those other cross sections in Ohio, namely the APLF, the thinnest, the 10-inch cross section that was highly modified HPM material all throughout in the APLF. Another way that we can look at it is using the stiffness ratio that was developed by NCHRP 944A. I believe that was Dr. Witzak that did that work. And I want to see if I can get down to a quick slide on that. Yeah, I'll throw that equation up real quick. So you should be able to see it now. This is that stiffness ratio that I talked about, and that we had done that work in the past as well for the other research projects. And so can also throw it into that equation. And really, we were just looking at the measured strain in the field to help us identify which sections were likely to behave perpetually moving forward and those that were not. As I mentioned, we did not do bending beam fatigue tests on this study, but as you can see in the cracking tests and the Hamburg test, that there's definitely a benefit of the HPM. We knew kind of from the work that was done at NCAT test track that there's believed to be a huge advantage in terms of fatigue endurance limit. Being that what Dr. Willis had developed at the NCAT test track with the cumulative strain distribution doesn't have to utilize the fatigue endurance limit. And so we relied on that. I think that's, oh gosh, more questions? Are there more questions?
There's one more question, Mary.
No, Johnny, no more questions from you. I'm kidding. Any lab performance data on long-term aged mixes? Yeah, no, we did not do any long-term aging as far as I'm aware. And Sam, maybe you can
No, we did not. You're right.
Okay, yeah, that's what I thought. We did not do any long-term oven aging. We just did short-term oven aging, but I understand that short-term oven aging is the best predictor of long-term aged material in terms of performance. So I think, yeah, we will probably see the crack resistance maybe go down for both materials, but with long-term oven aging. But again, I think we'll continue to see that benefit with the HPM. So I hope I answered the questions. They said, you know, that stiffness ratio was sort of just a check. We weren't really reliant on that. That's something I just wanted to add to it for context, because it is something that we looked at in the other perpetual pavement sections, and that's how we arrived at, yep, it looks like these sections were behaving perpetually in the field. We want to use those sections to lock in what our threshold should be to design these new sections, and then compare those new sections back to our designs, compare that string in the field also back to how those other sections performed under similar conditions. And that kind of helped us identify which ones were to be perpetual. And mind you, the 8 1/4, the thinnest cross section, was not intended to be perpetual. And we knew that going in. That was what the rest of the main line was going to be. I don't know, Sam, if you addressed that or not.
So that was section 7 in the design. And if we looked at the, if you had seen from the handout, the section design, you can see that 7 matches the main line on both ends. So yes, it wasn't intended to be. The strains that we got were in the lower end. We expect it to be, again, tree cover, lower temperatures, more uniform temperatures with those pavements. So not going through the big swings, except for section 5, all contributed to, having all these sections kind of perform the same.
Are there any differences in in-place air voids of the HiMA compared to the conventional? And that's a great question. I don't have that data in front of me to give you a good answer on that. And I'm not sure that, I know we were not able to include that in our analysis. It would have been nice to look at that. Certainly, in-place air voids are very critical to the durability in the field in terms of field performance. So I suspect that, some of the differences that we're seeing in strain between sections are probably related to in-place air voids. Unfortunately, we weren't able to normalize for that or to really account for that. And, because we're so limited, and I want you to feel like, I know some of this data that I'm talking about isn't in front of you, but because of the comprehensiveness of this project, it was just quite large. And the time that we had today, we weren't able to really go in depth in terms of the design and then the analysis of those field measured strains. But hopefully, the report will be out at some point. And, once you read it and you have questions, you're free to contact me and we can have some discussion on that. But no, Jason, sorry, it was not, and we didn't have it available.
They were very close to each other, Mary.
Were they? Okay, good.
All right, thanks so much. Our audience is saying great webinar, thanks. Yeah, and Jen, any other final comments from the research section?
No, I don't think so. Thank you guys so much. This was a great presentation. And you guys did a good job cramming a lot of information into a short period of time. So thank you. And thank you for everybody that attended.
Thank you.
Thank you.
Thank you.
Thanks, everybody. Have a good day. Bye.